Hi class, we are now on chapter 7.3, first law of thermodynamics. The first law of thermodynamics has to do with the law of conservation of energy. It is thermodynamics, first of all, is study of energy and its transformations into conversions, if that's another way to put it. The first law has to do with energy. It means that there is a total amount of energy and it stays constant. You cannot create nor destroy energy. It will be transferred into something else, something that we may not always be able to detect with our eyes, but it is always constant. There's nothing that you can just make up out of nowhere. Now we're going to discuss internal energy. The internal energy is the sum of the kinetic and potential energies of all the particles. Now, all the particles that compose a system. And when I highlight particles, what I mean is the kinetic energy not only includes the motion of the molecules inside the system, but also the motions of the atoms and the subatomic particles that are within these atoms. So it's everything in its entirety. The change in the internal energy of the system depends only on the amount of energy in the system at the beginning and the end. So the initial and the final. This is called a state function, meaning it doesn't matter how you got from point A to point B, just that we're going to consider point A and point B only, not the path that it took to get there. So when you look at this is a change. This triangle is called delta. It means change. So this is change in internal energy, and we are only interested in the internal energy of the final in the system and the initial in the system, or the internal energy of the products minus the internal energy of the reactants. So here's another definition of state function. Here is two paths, path A and path B. One is longer than the other, but when it comes to a state function, we don't care. We are not interested in how long it took you, how many miles. We only care that you started at one spot and you got to the ending. That way we can subtract the final minus the initial. Nothing to do with it took you 12 hours versus it took you 7 hours, and so forth. A state function only cares about initial and final conditions. Okay, so now we're going to start looking at energy flow and having to do with the conservation of energy. So conservation of energy requires the sum of the energy changes in the system and the surroundings must be zero. So remember when I showed you guys that fun little roller coaster and I told you that the total, imagine a value, and that value, the total, is the sum of the kinetic energy and potential energy. This is now we're going to be talking about system and surroundings, but try to imagine it's very similar to that. It's got to have a certain amount and it doesn't change from that amount. So this is where the energy is not created nor destroyed. You just can't randomly throw numbers out there. You have to figure out where they come from. And if you take from one thing, that means that it's being added to something else. Okay, so when we take a look at this, it's saying that the system and the surroundings must be zero. What that means is that the change in internal energy of the universe is equal to zero. How can it be equal to zero if you're summing up the internal energy of the system and the internal energy of the surroundings? Well, you make them equal to each other, and which is what I did down here. One will be positive, the other must be negative. You have to have a value, and it has to be equal, but in the different direction. So meaning negative or positive for the other side. Okay, so let's take a look here. We have, think of these are like gas gauges. We have a system and we have a surroundings. And what we have before anything's happened, it looks like this one has the system. The system itself has half a tank full, half a tank empty, depending on how optimistic you are. And then in the surroundings, we have a quarter. So something's going to happen here, and that means that one is going to gain and the other one has to lose the same exact amount. So after something's happened, we look here and we see that the system has lost a quarter. That means that that quarter has to be accounted for into the surroundings. It was transferred, that energy was transferred into the surroundings. And the negative and the positive sign indicate the direction of where that went. As long as you understand what the system is and the boundaries of a system and the boundaries of our surroundings, this is not difficult to understand. Okay, so, and if it is, I have some examples. Energy diagrams. Energy diagrams help you see the internal energy and what's actually happening during a reaction. So this arrow goes up. That means that there's an increase in energy. So anything down here and anything below it is low in energy. But as you start going up like in stairs, that's higher and higher energy. Remember I told you in chemistry, everything wants to go to its lowest stable form. And in order to do that, you release energy. So in this case, we have a reaction. I'm not going to go into the reaction right now. But what you notice is that you have a higher level for the reactants than you do the products. This means that the reactants have higher energy than the products. And energy had to be released in order for this to get down here. Plus there's a big red arrow that's telling you the direction of how this went. So even if you didn't have anything else, look at the arrows. The arrows will tell you. So this means that the arrow is going opposite. There is a decrease in internal energy. That means it's negative. Why is it negative? Because the decrease means that there's a value that was released that's less than 0. So it's a negative value here. There's a number, but the negative makes it less. So that's telling you that the energy was released, and the more stable is the products over the reactants in that. So here we have a system, and there's an arrow again. So the energy that was released went into the surroundings. So when that value is negative, that means that and it's regarding the system. That means that the heat, let's say heat, the heat was released into the surroundings, and the surroundings become positive because they took that. Now, if so this is why the surroundings are positive. So think about it this way: I have $5, and I give somebody that $5. I am now out. I am negative $5, but the person I gave it to is now positive $5. That's exactly what's happening here. And here's another one. So if we look at this energy diagram, we see that same thing. As it goes up, its internal energy, we have a reaction. The reactants now are lower than the products. This means that this is going to be positive. Energy has to be taken from the surroundings into the system in order for this reaction to occur. This reaction will not occur without more energy to push it forward. And this is something like ice melting in a sense. Your hand turns cold because the ice is an endothermic reaction, and it's taking the heat from your hand and transferring that as energy into the ice. So that's similar to this. It's going from the surroundings, and your hand being the surroundings because you're simply holding the ice, and the ice is pulling the energy as in the form of heat from you. So in this case, the ice, if you want to look at it this way, the ice has become positive, and because it's not a negative number, because it's taking something. And then the surroundings, my hand, the energy's leaving. So in this case, let's reverse it. I now take my $5 from this person. I am positive $5, and I am the experiment. I am the system. And the other person is the surroundings. That person is now negative $5. Okay, so now let's break down this reaction itself. So the total amount of internal energy in 1 mole of carbon, solid, and 1 mole of oxygen, gas, is greater than the internal energy of 1 mole of the product, carbon dioxide. So what this is saying, the internal energy, this is the same one we looked at on the other page, the reactants contain higher internal energy than the product. So it's always going to go towards the lowest stable, my mind just went blank, the lowest stable form. And that means it's going to release that energy so that it can take on a stable form. Well, that energy has to go somewhere, so it's going to go into the system, and it's going to be removed as this reaction takes place, because this reaction can't take place with that excessive energy. It has to be removed. So in this case, it's being negative in the reaction because the reaction is releasing that energy, and it's positive into the surroundings because it's going into the surroundings. So that's what this negative and the positive means. But what if it's the other way? So if we look at it this way, and we have this as products, the solids, and we start with CO2, so this is a decomposition, right? In this way, it takes more energy to get to the products, to decompose into the elements that it was, or products. In this case, we need to take energy out of the surroundings and place them into the system to make this reaction go. This reaction, because it's not energetically favorable, because it has to be lower in energy, that means it's going to have to take energy from somewhere to push this forward. And in this case then, if you look, the surroundings are negative because the energy's been taken out of the surroundings, much like my hand with the ice cube, and into the reaction, the system. So this is just pretty much the same thing I've already said. When energy flows out of a system, it must flow into the surroundings. Everything has to go somewhere. And when energy flows out of the system, it is negative. If you have a hard time figuring this out, this is the best way to understand this. Think of a checking account. Hopefully you guys have checking accounts, you have a piggy bank, you have something. When you make a deposit into your system, which is, let's say, your bank account, then that money is positive, it's being credited into that account. But when you pull money out, it is negative. You're taking that money out of the system and you're going to use it in the surroundings somewhere. That's exactly what this is. So if you start getting confused about this, think of a bank account. When you put money in, it's plus, it becomes positive. And when you pull money out, it is negative, and you're going to go use that money in the surroundings. So that's a way to visualize what's happening here. And that's what this is. This is my bank account. I just pulled $20 out, and I'm going to take it here, and I'm going to go use it, I don't know, wherever. Okay, so one has to equal the other, and the negative and positive sign will reflect which way this is going. There should be a negative positive sign here. Something is not there. There it is. Pretend there's a negative and positive sign here. So what this means is that this is going to be negative right here. There's a little negative. So everybody make note there's a little negative here because the energy flow is out of the system and into the surroundings. Okay, and then I'm going to make a deposit of money. I'm going to deposit that money. That is a positive thing. Sure, it makes me broke. I have no money on me, my person, but I have money in the bank account. That's how you want to look at this. It is negative in the surroundings. I can't go to McDonald's and get something, but I have money in the bank, and that's a good thing. Okay, so summarizing energy flow. If the reactants have a higher internal energy than the products, the system is negative, and the energy flows out of the system into the surroundings. Why is that? Because the products will have lower energy, and it cannot hold on to that excess energy. If the reactants have a lower internal energy than the products, it's positive, and it needs energy in order for that reaction to occur, and it's going to pull it out of the surroundings. Okay, so let's take a look at another one. Consider this fictitious internal energy gauges that describe the initial conditions for a chemical system and surroundings. So we start with a system that's almost full. You got an almost full bank account, and the surroundings, you and your person, you don't have that much money, and you need some money. So what happens here? What energy gauge corresponds to the final conditions following an energy exchange in which the system is negative? So here we go. The first thing you need to do in order to understand a question like this, what is the system? What is the surroundings? Let's talk about a bank account. You have a checking account. That would be the system. So if something negative is happening to your checking account, that means you're pulling money out. So something is leaving your checking account. So now that we understand what's happening, that means that this is being pulled out. Something from here is going to leave and go into my wallet, which is the surroundings. So here, let's take a look. This one filled up more. That's wrong because we didn't make a deposit. This one went down. So this is a good one, but this one never changed. Energy cannot be created nor destroyed. So this is not accurate. This is a lie. And then here, it was added to the surroundings. So it's even and even. I had $40 in the account. I took 20 out. So now my bank account is 20 and I have 20 and everything, life is good. So this is a good example of where the money went. And that's A. Okay, so energy exchange. Energy is exchanged between the system and the surroundings through heat and work. Q is heat, that's thermal energy. Work is W. Remember pushing a box? Q and W are not state functions. That means that it does matter how they get to where they're going. It's not just a path of A to B, final minus initial. We need to know everything that's going on in order to use it correctly. So it's not a state function, even though internal energy is. Okay, so let's take a look at, understand what a system is, understand what our surroundings are. Then this does not become complicated. And use something that you can think of, a visual box if you have to, checking account, something. So Q, heat. It's positive if a system gains energy. This would be an endothermic reaction. This is an ice cube, pulling heat out of my hand. A system loses thermal energy. This is a hot cup of cocoa. I'm losing the heat, and now my cocoa is getting cold as I sit there. W, work is done on a system. This is a piston. Oh, no, excuse me. Let me think of a good example of this one. Okay, this is a piston, but the piston, or think of like a lever inside an enclosed tube, if you guys don't know what a piston is. And the surroundings have pushed the piston down. That means that work is being done on the system from the surroundings, and that's why the surroundings, which would be the system, is negative, because it's pushing into the system. And it would be opposite if that piston gets pushed up because of a combustible reaction inside that piston, pushes that piston up. That means that there's work being done by the system, and it's going to be released from, so it's negative on that system, but positive to the surroundings, because the surroundings are taking that excessive energy as work. So, if internal energy, the change in internal energy, if the answer, the value, ends up being positive, that means that more energy flows into the system. And if it's negative, energy, the overall energy has flowed out of the system. And it can be in the terms of Q and W. So energy exchange, I found one for heat. It's a lot easier to explain with heat than it is for work. So in this case, Q, energy is exchanged between the system and surroundings. So I found this lovely picture. Here it is. The ice cube is the system. So you can see heat going into the system. This is an endothermic reaction. This would be Q. So this is going to be positive. But heat being released out of a system is exothermic. Think of fire. You're just sitting in front of a fire, and the heat is being released from that. That's going into the surroundings to warm the room. That is negative. Okay, so heat and work. The white ball has an initial, so we're going to look at a pool table. The white ball has an initial amount of 5.0 joules of kinetic energy. As it rolls on the table, some of the energy is converted to heat by friction. The rest of the kinetic energy is transferred to the purple ball by collision. So what this is saying is that the ball moves. And as it moves, it's on a trail. But in that trail, the friction of the ball being on that material, that felt, is being released as heat. So it's not complete kinetic energy as in motion. It's being released, or work. You want to look at it as work. In this case, you're actually losing a little bit from heat. Think of like, if you rub your arm on a material, you'll start feeling heat from it. That's friction. So if you're losing that into the table. So not all of that 5.0 joules is going to be transferred because you just lost a portion of it in heat. So this means the energy lost by the first ball is going to be positive into the system. Wait, no. Positive energy gained. Why is there a negative sign here? Hold on. Okay, this is a mistake. This should be positive. This should be negative. You can disregard this slide because I'm going to cover it in the next one anyways, but you should make a note that this is positive because it says right here, energy lost by the first ball. Their energy is leaving the white ball, and it's going to be converted. It's already been converted into heat from the friction, and it's then going to be converted into the collision with the purple ball, which will cause the white ball to stop at zero. So it's lost all of its energy. So in this case, this is wrong. This is not going into the surroundings because the surroundings didn't give energy to the white ball. It's opposite. The white ball lost its energy and the surroundings took the energy. So make a note on this one. I'm going to cover it again right now anyways. So let's take a look at two examples. On a smooth table, most of the kinetic energy is transferred from the white ball to the purple ball. This is a smooth felt table with a small amount of loss through friction. So if you start at 5.0 joules, and we look at initial minus final, the initial is 0 because the ball is at a complete stop now. So it is negative 5.0 joules. That's correct, right? Because it lost energy to the surroundings. So it should be negative, and the magnitude of it is 5.0. But now we have to look a little bit more in. We need to know internal energy is equal to Q plus W. So now we need to designate which one and what values go to Q plus W. Well, we just learned that friction, this little arrow is going down, we lost 0.5 joules. So if we start out with 5 and we lost 0.5 joules, then that means that the kinetic energy that was transferred to the purple ball is 4.5 joules. The total has to be 5.0. We have to figure out which direction it is, but the values itself is 5.0. That means that my heat and my work have to match up to, they have to sum up to 5.0, and they do. So there's a negative here because we released heat into the surroundings, and there's a negative here because we released the work onto something else. Work was not done into the system. Nothing was credited or deposited into the system, only releasing. So this is where on a smooth table, the overall internal energy is 5.0, but the internal energy change is negative because both work and heat did work on the system and it was transferred into the surroundings. Now let's take a look at a rough table. So now we expect more friction, which means that the value will be even more because more heat's going to be generated because this is not a smooth surface. Now, kinetic energy is still 5.0. Remember I told you those numbers don't change, but the values of Q and W definitely will. So in this case, we determined that the kinetic energy that was transferred, energy of motion, is 2.0 joules. So if it's 2.0 joules, then that means that 3.0 had to have been lost as Q in heat friction. So when we plug those in, energy is still released, but now it is released in different values. Q lost more heat to friction than it did in movement. We transferred less movement to the purple ball, but the value of internal energy stayed the same for both conditions. Okay, I found this from another class I taught. This gives a nice little visual so you can see when work goes into the system, it's positive. When work goes out of a system, it's negative. And when Q goes into a system, it's positive. And when Q goes out of a system, it's negative. Okay, heat, work, and internal energy. In the previous billiard example, we looked at the white ball for both cases of Q and W. On the rougher table, there was a greater heat loss, as in Q. It's a negative number. The rougher table, less kinetic energy was transferred, which is something I already told you. So the work done by the white ball had to be less, because remember, the final value has to stay the same. So the only thing you can change are the conditions within it, but the final numeric value doesn't change. So in this case, work was done, the energy of motion was less for the rougher table. The change in internal energy is a state function. It only depends on the velocity of the white ball before and after the condition. In both cases, it started out with 5.0 kilojoules and it ended with 0. So how it got there was not a concern for internal energy. He left it up to heat and work to figure that out. And heat and work, they are not state functions, so that does matter on those. All right, so which heat exchange is best classified as work? An ice cube melts and cools the surrounding beverage. A metal cylinder is rolled up a ramp. Steam condenses on skin and causing a burn. In this case, this is work, so it's going to be B. There's some work happening, motion. Remember, this is motion. It's easy kind of remember like kinetic energy. It's motion that's going on. So it's going to be B. And then here is another problem. A chemical reaction is performed in a flask that is connected to a piston. Heat is allowed to enter or escape the system, but matter cannot. The reaction releases 890 joules of heat to the surroundings, and the gas produced performs 450 joules of work on the surroundings by pushing the piston. So we need, which I obviously forgot to put here, is to calculate the internal energy. So I put it up here. Again, from another class, I filled in the values. It uses U, so disregard that. Another textbook I used U, but we are using E, so this is still internal energy. That book said U was internal energy. Most books use E. First thing you have to do is pull out the information you have. Even before that, understand what's being asked of it. I, of course, left that important question off here, so I'm going to tell you what it is. Determine the change in internal energy and what direction it's in. So we have reaction releases heat. So we keyword heat, so that's Q. It says releases, that's it, out of the system into the surroundings, so that's negative. And then it says that the gas also performed 450 joules of work on the surroundings. So that means that work was done by the system into the surroundings. So that's also negative. So we have Q that did work from the system into the surroundings, and we had W that also did work from the system into the surroundings, on the surroundings. So both these values are negative. We plug them in, and it ends up being negative 1,340 joules. That is the change in internal energy from this reaction. That's it.